In this video, I will discuss with you a very interesting compound, one that's been historically known for a long time, but which caused quite a bit of controversy in terms of its structure when it was first discovered, and that is a compound called benzene, having the formula C6H6. Benzene was discovered very early on. It's very easy to obtain from petroleum and lots of other places, and it was known almost immediately that it has the formula C6H6. But the structure of it caused quite a bit of controversy because remember, in those days they didn't have instruments. They couldn't stick it in an NMR, they couldn't stick it in an IR to get the kinds of bonds and so on. So they had to do it all by thinking it through and doing experiments and isolating different products of different masses, so on. Well, they knew the structure was C6H6, but right off the bat that caused a lot of consternation, just the formula. And why would that be? Well, remember the index of hydrogen efficiency. If you have 6 carbons in the molecule, how many hydrogens would it have if it was saturated? Remember the 2n+2 rule? It should have 6 times 2 plus 2, which would be 12, plus 2, which would be 14. It should have 14 hydrogens. It only has 6 hydrogens, so it's missing a bunch of hydrogen. In fact, 4 pairs, so its index of hydrogen efficiency is 4. And that suggests that it has either 4 double bonds, or 4 rings, or some combination of 4 double bonds and rings together. And that's a lot for such a small number of carbons, only 6 carbons. And that meant that people knew almost immediately that there's got to be something wrong here, because either it's going to have a lot of double bonds, or it's got to have a lot of rings, or some combination. Both of those were a problem, because two of the properties of benzene that we want to talk about are these. First of all, it doesn't react with hardly anything. It doesn't react with HBr. It doesn't react with water and dilute acid, both of which it should if it was an alkene. So if it had double bonds, or even triple bonds for that matter, it should react with water and acid to form alcohols, and it should react with HBr to form alkyl halides. In fact, benzene didn't react with them. It doesn't really react with much of anything unless you treat it under very strong conditions, which leads us to the other property of benzene, which was that it was very stable. In other words, low in energy. Remember how when we talked about alkenes and conjugated and non-conjugated and so on, 2 of the measurements you can make are heat of combustion and heat of hydrogenation, both of which are exothermic, give out energy. And the more energy the molecule has to begin with, the more energy will come out when you either burn it or hydrogenate it. When you burn benzene, you get out way less energy than you otherwise would expect for a compound with 6 carbons and 6 hydrogens. So it's really not a good fuel. It doesn't give out very much energy, and thus it means that it must be pretty stable or low in energy to begin with. Same thing with hydrogenation. If you can even manage to hydrogenate it, which is difficult, but you can do it, and if you do hydrogenate it, turns out you get out some energy, but not nearly as much as you would otherwise expect. So in other words, the properties of benzene are that it's very stable and unreactive, especially unreactive with reagents that normally react with alkenes. So, cut right to the chase, there were 2 proposals for what benzene could possibly be, having a formula C6H6. One of which is a prism type shape, which was proposed by a guy named Dewar. No double bonds, but actually having 4 rings, 2 3-membered rings in the structure, and then 2 4-membered rings in the structure. So that would be, and they even knew it at that point, that would be highly unlikely, because it has a lot of angle strain, so it should be high in energy, not low in energy, as we know benzene is. And it's kind of unfortunate because Dewar, who was the scientist who proposed that structure, was laughed at for it, because they knew it would have to be too unstable if benzene couldn't actually have that structure. And his career was kind of ruined by that. And he never actually proposed that was the structure of benzene. He proposed it could be the structure of benzene, but he immediately rejected it himself, and yet his name became attached to it, and people tend to laugh at Dewar because it doesn't make any sense that would be the structure. However, we'll see that there is something going for it here in just a minute. The other structure that was proposed was that of a guy named Kekulé. He proposed a 6-membered ring with 3 double bonds in it. Again, that didn't really fit the bill, because having double bonds, it should react with HBr, and it should react with water and acid catalyst, and it does neither. So it also doesn't really fit the bill. But it turns out the Kekulé structure is correct, as we'll talk about here in just a minute. But what I want to do at this point is discuss with you a little bit about how did they how did they come up with these two structures, and how did they reject other possible structures? Because in fact there are some other ones, and you might want to see if you can draw other structures of formula C6H6. But those were the two that were settled on, and here's why. It turns out that if you work really, really hard and you try to find all the compounds in the world that have the formula C6H4Cl2, which people recognized immediately was really just like benzene, except two of the hydrogens had been replaced with chlorines. Obviously then it becomes C6H4Cl. It turns out that there are only 3 compounds in the world that have that formula, so 3 isomers were discovered. Now that doesn't necessarily mean that there are only 3, because it's possible, even though they worked really, really hard to find all the possible structures, that for whatever reason they just never found some. But it's pretty clear that there were only 3 possible, there were only 3 isomers that had been isolated, 3 different compounds, all of which had the same formula, but had different properties, so they knew they were isomers of each other. So what you should do, and I want you to pause the video here for a minute, is see if you can draw, based on a Dewar model. So go ahead and draw that structure 3 times. See if you can draw, and put 2 chlorines onto this skeleton 3 different ways that would all be different from each other. Okay? And then same thing here, see if on this skeleton you can put 2 chlorines onto that skeleton, and again draw it 3 times. And see if you can find 3 different ways of putting 2 chlorines onto that skeleton. Okay, so pause the video for just a minute and do that little exercise. And then also convince yourself, are there more than that? Are there more than 3 ways that you could put 2 chlorines onto this structure? And then are there more than 3 ways you could put 2 chlorines onto that structure? Okay. I'm back. I'm going to solve the problem for you now. Hopefully you paused the video and worked on the problem yourself a little bit. But let's go ahead and draw them out. Okay, so how could we put 2 chlorines onto a prism type structure like this? Well, you could put them on like that, which would be the same as putting them on here and here, or here and here. So that's a possibility. You could put them on like that, right next to each other, on a 3-membered ring. That would be the same as putting them on here and here, here and here, here and here, here and here, or here and here. And then there's the other 3rd possibility, and that would be chlorine here and chlorine there. That's different from the other ones. And then there are many other ways that you could have them that would all be equivalent to this one as well. There are 3. Turns out there are no more than that. And if you think you have more than 3 possibilities, I think you'll find that at least 2 of them are the same as each other. Okay, so those are the 3 ways. And so that fit with the fact that there are, in fact, isolated in the real world, 3 different compounds with that formula. So Dewar proposed that as a possibility based on these structures right here. He didn't mean that that was the actual structure of benzene. What about on calculate benzene? How many different ways could we arrange them? We could arrange them straight across from each other. We could arrange them in an M-type shape, sort of zigzag pattern like that. Or we could arrange them right next to each other. And so there's 3 possibilities there as well. But some people at this point said, but that doesn't work, because in fact there's a 4th possibility for calculate benzene with 2 chlorines on it, and that would be if we switch the double bonds around and put the chlorines on like that. Would not that be a different structure? Because here the 2 chlorines are attached to carbons with a single bond in between them. Here the 2 chlorines are attached to carbons with a double bond between them. So there should actually be 4 different isomers, and therefore that can't be benzene. That was the argument in those days. What we now know is that the fact that you can draw a 4th possibility actually explains why there are only 3 possibilities and why they're so stable. Because it turns out, in fact, these are resonance structures of each other, not different compounds. And so there are really just 3 possible isomers, not 4. So it fits with the fact. And it also explains, if we can draw more than one resonance structure for any aromatic compound, and that's true for benzene or anything else that has that 6-membered ring with 3 double bonds in it, you can always draw, no matter what's attached, you could draw a resonance structure with the double bonds in that location, or you could draw a resonance structure with the double bonds in those locations. And notice that these are in fact resonance structures of each other. And that, because you can have more resonance structures, therefore it's more stable, and that not only explains the fact that there are 3 isomers, but also explains the stability of the molecule. And because it is so stable, it doesn't want to break up the fact that you can draw 2 resonance structures, and therefore that explains also why it's unreactive. So that's kind of the theory that was settled upon soon after the first 2 structures were proposed for benzene. One little detail before I finish here, are these 2 in fact resonance structures, or aren't they really just the same thing as each other? Well, they're the same thing as each other, but in order to make them be the same, you have to turn it over like a pancake, and you're not allowed to do that with resonance structures. Remember, resonance structures, they're frozen in space, and what you're doing is looking at all the ways you can arrange the electrons in the molecule when the atoms are frozen in space. And so they are in fact resonance structures, even though they're the same as each other. And we've come across that situation lots of times where you have 2 resonance structures that happen to be the same as each other, but they're still resonance structures of each other. Unlike isomers, where if they're the same as each other, they're not different, they're just 2 different ways to draw the same thing. With resonance structures, they are in fact considered to be different resonance structures. Okay. All right, we'll stop at that point, and we'll deal with more aromatic stuff in the next video. Thank you.